My name is Bjarne Sørensen from Philips Medisize. I'm here to talk to you about the ARIA platform device that we are developing at the moment. It's an electronic platform compared to the traditional spring-driven autoinjectors out there. So I'll tell you something about the differences between the way we do it and what performance options we have versus what is currently out there in the market. The evolution of devices is happening out there. In the early days, it was syringes and vials that was used in the hospitals. And when gradually treatments were moved to the homes, autoinjectors, prefilled syringes, and injection pens found their way into the landscape. And currently, there's a development going on where pharma companies are searching for a platform approach. And that also means that from the sustainability initiatives, reusable autoinjectors and pens will find their way into the landscape. And that is exactly what we are going for. We have 4 cornerstones in the concept for the ARIA platform. One is that it should be as small and easy to use as the current devices out there. So it's really a 2-step autoinjector that, as you know, we have the advantage that we have graphical illuminated icons combined with the audible sounds that provide a really good guidance for the patient. When the cassette is inserted, it's similar to the operation of the current disposable autoinjectors out there. Take the cap off, put it toward the skin, and then remove it when the injection is done, and you can dispose the cassette. It is a platform for the pharma industry because it has this huge power reserves. We can use the electronic motor and the drive system to control the forces and the speed of the plunger so that we get this gentle engagement with the stopper and have a really controlled system that has a quite significant force available. It's including connectivity. We have Bluetooth connectivity included, and it can interface to our connected platform, but it can also interface to other connected platforms out there. And we have really minimized what is the waste per injection. Also, the size of the cassette means that the packaging will be significantly smaller than the current devices out there. So it's really have a completely different level of sustainability compared to the current market offerings out there. Small and easy to use. It's working almost in the same way as a normal sleeve-triggered autoinjector. You put the cassette in, you take the cap off, you put the autoinjector towards your skin and wait for the end of dose signaling. And then you can lift it and then remove the cassette and throw it away. So it's really as simple to use as possible. By using an electronic motor, we can handle all 1 ml and 2.25 syringe types, and meaning that we can also handle very low viscosities and very high viscosities. So it's really a platform that enables the pharma companies to have one device that can handle most of their injection needs. There's one unique thing about this, and it is the fact that our end of dose signal includes the dwell time. Typically, there's always a few seconds after the injection is finished where you need to keep the injector in place to avoid what is called a wet injection, as a drug lifting or leaping out on the skin. We automatically can have that dwell time included in the end of dose signaling, which gives us a big advantage. The platform consists of 2 elements, the intelligent reusable drive unit and the single-use disposable cassette. As mentioned, we have an electronic system, so it's really a high-power motor that is controlled by a microcontroller that enable us to give up to 120 newtons of force, meaning that we can handle really high viscosity drugs. We can do the full dose delivery in 10 seconds. It's a setting we can do in the system so we can adapt to what is required within limits. It's a simple sleeve-triggered operation, and it has a visual and audible user interface. We have a 3-year service life, and it's a rechargeable battery that's inside it, and we have the built-in Bluetooth low energy connectivity. The cassette 1 and 2.25 prefilled syringes can be handled. It's a standard subcutaneous delivery. We have needle safety before and after the injection. And as mentioned, around 50% less waste and storage space compared to disposable autoinjectors. We have the large operation inspection window, and we have an opportunity for including RFID in the cassette. You can see that in the label there's a RFID tag, and we have an RFID reader in the device, so we can also, with connectivity, transmit the actual batch number and lot number of the cassette, the syringe, for example. This is an overview of the ecosystem. You can see we have the pre-filled syringes, 1 ml and 2.25. They go into the same type of cassette. And then we have a drive module that is the electronics and all the necessary bits and pieces that is required for this device. And the same driver module can be used with an ARIA Basic, which is the top one on the left. And then we can do customized versions of the ARIA Basic. And then we also have what we call ARIA Plus, where there's a graphical user interface, meaning that we can do more advanced operations with the device. It's the same drive module, but we can configure it in different ways. And it's the same drive module that is used for all the syringes and viscosities. Looking a bit into the sustainability aspects of the ARIA program, we have compared it with disposable auto-injectors, and we have done a full life cycle analysis of the system, including all the way from cradle to grave. So it's the complete use aspects of the device compared to the current way of doing injections with the disposable auto-injectors. We have used a weekly injection for the 3 years of lifetime, which give 156 injections in this example. Of course, we would need to do a calculation depending on the actual use pattern of therapy. But as you can see, for 1 ml, we have a 34% decrease, and for the 2.25, we have a 51% decrease. The 2.25 ml auto-injectors are bigger and heavier than the 1 ml because the spring forces needed is approximately 4 times the force needed for 1 ml. So it inevitably will be bigger. And you can see the different aspects: logistics, production, recycling, etc. It really gives us a good understanding of the system by doing an LCA early in the development of a product. If you look into the span that is required if you want to handle both 1 ml syringes and 2.25 ml syringes with the same device, and then also different viscosities of drug, you will see that there's a big difference between the load on the device for doing 1 ml 1 centipoise and 2.25 ml 20 centipoise. So it's a really big it's a challenge for a spring-driven device to be able to do that. Here you can see we have done it with this 27G thin wall needle, and this is just examples of the different requirements that you are facing with if you want to handle 1 ml and 2.25 at the same time. If you look at the drive module setup we have, the principle is that we have an electronic motor drive. In the motor, there's an integrated planetary gear, and then we have a gear to drive the lead screw. We have an encoder on the motor axle, so we can know with the microcontroller exactly where the plunger is in the stroke. We have done our embedded drive control algorithm that is embedded in the microcontroller, and we can set different parameter settings in this firmware so that we can set a force limit, and we can set a time injection target and different other aspects that we can adjust to. We have a rechargeable battery that has a high current capacity so that we can do the high forces required. And then by having an electronic system, we can also connect the drive module to a readout. And then after use, we can actually read out all the injection data that is being stored in the device, which is really helpful for us also. And for the pharma company, if we get devices back, we can read out what has happened out there in the real world. The preliminary performance data we have is that we have set 120 Newton as plunger force. Our algorithm is built up in the way so that we have a constant injection speed target, for example, 10 seconds. And then we can vary the plunger force as required to set up the limits in the firmware to what is required. We have current limits and we have max motor RPM limits also settable in the firmware. We are independent of syringe fill volume because we are just moving the plunger at a constant speed throughout the stroke. So it does not matter if the syringe is fully filled or half filled or in between or whatever. In that way, we do not see excessive forces when the stopper reaches the plunger. It's a really big difference between spring-driven devices. They will have a high impact force when the plunger hits the stopper. Come back to that later in the presentation. It also means that we have no issues with the variations in the break-loose force or gliding force. That is inevitable that there will be differences in that, but our force headroom is so high that we can overcome that quite easily. It also means that we can handle non-siliconized syringes as well. And by having the setup in the way we have, it also means that we can handle multiple drugs with the same devices if that should be a requirement. If we dive into the technical bits and pieces here, you can see curve where we have on the x-axis we have the ejection time, on the y-axis we have the plunger force. You can see the force limit of 120 newtons, and then you can see what injection times and forces we will reach with different viscosities of drug, from 1 centipoise to 80 centipoise in this case. This is a 27G thin wall needle this is shown with, and 29G thin wall, but 1 ml for both. And you can see the 120 Newton force seems high for a 27G thin wall, but when you see the 29G thin wall, you can see that the max force we have sort of fits with the typical upper limits of the viscosities that we will see. So what you also can read out of this is that we can actually go with a thinner needle and still have the possibility to do the injection with a very short and determined time. It's quite the impressive performance envelope, and it really means that from the pharma company point of view, they can sort of, the sweet spot is the 29G thin wall, and then we can handle all the coming viscosities within a decent injection time. So, conclusions. It's really evident that this ARIA program, it offers completely new opportunities for the pharma industry because we have this very comprehensive performance envelope. We can deliver drugs over a very wide viscosity range, keeping a constant injection time with the same setup, and it really creates a flexibility for pharma to have one device that can handle all. We can handle both 1 ml and 2.25 pre-filled syringes by the same device and cassette platform. The forces we have available in the system also mean that we can, the pharma industry can optimize towards thinner needles and then benefiting the comfort of the patients. And the force headroom also mean that we have no issues with the inevitable variation in break-loose force or gliding force. And the system is also applicable for non-siliconized syringes. We have no high impact stresses on the syringes due to the constant plunger speed at the stopper engagement. Also, the possibility to have partially filled syringes, and I have full flexibility on that without any issues. It's a completely different system compared to what is known out there today, but it has a really significant performance aspect available. Beyond that, we have the real advantages regarding sustainability and waste per injection. We have the already embedded connectivity options. Having connectivity in a disposable element is, from a sustainability perspective, a really, really tricky thing if it's in high volumes. We have the ease of use for the patients with a very simple operation, and then the potential to use the same device for multiple drugs. It would be an even better sustainable solution, also very cost effective by using the same device maybe for 2 drugs as used for the same treatment or related treatments. I think that was it, and if you have any questions, you are welcome to contact us. There's also a possibility to dive more into the performance aspects of the ARIA device in the On Drug Delivery magazine, and there's also 2 articles regarding sustainability in the On Drug Delivery archives you can find if you search for it. Thanks a lot for your time.